Hey, welcome to our second day of optimization notes. Now, this problem we have right here for optimization is definitely one of the tougher ones, but I'm going to show you how to do it pretty much exclusively on the calculator and how it can help you out and benefit you no matter what the question's asking. So I'm actually going to add a couple questions to this so that we can get more of a feeling of how helpful that calculator is if you use it correctly. So let's get through this question, and it's going to get a little kind of confusing until I draw the picture, so let's get through it. So we got a man who launches his boat from point A on a bank of a river, which is 3 kilometers wide, and wants to reach point B, which is 8 kilometers downstream to the opposite bank as quickly as possible. So pretty much river right there, drew it in blue because it's a river. And then we're at point A. And again, this river is 3 kilometers wide. And they want to reach point B over here. So what's as fast as they can reach here? Now, this is going to give us some options. He could row the boat directly across the river to point C and then run to B, or he could row directly to B, or he could row to some point D between C and B and then run. So essentially, these are his options. He can either row his boat gently down the stream and then run, or he can just row his boat right to point B, or he could row his boat to some point D and then run. Now, why does it make a difference? Well, he's rowing at 6 kilometers per hour, but he's running faster at 8 kilometers per hour. So for those of you thinking, oh, just row straight there, well, he runs faster than he rows. And then so he can grow all the way to B, or he could just row as little as possible and run as much as possible, or he can do a little bit of both. So that's essentially what our question is asking here. So we're looking for as soon as possible. So we're looking to minimize time. So we want to minimize time. Okay, so let's go ahead and look at our time formula. So time is going to be the amount of time that he is rowing plus the time he is running. Now, in order to get what these formulas are going to look like, you need to understand that distance is equal to time times rate. That will always give us our distance. Okay, you may have learned that in physics or just kind of a little bit of common sense there. So the time times the rate is how far you go. So if you're going 30 miles per hour and you travel for 2 hours, then your distance is going to be 60 because you multiply that. All right, so let's solve for time. So time is equal to distance over rate. So we need to find the distance over rate for rowing and the distance over rate for running. Okay, so how are we going to do this? So for rowing, do this in a different color. So for rowing, time is going to equal the distance. I'll find that in a second. And it tells us the rate right here is 6. So now the distance. So I don't know how much I'm rowing, so I'm just going to use just this path right here just as a generalization. So I do know that this part is 3, and I do not know how much that is. So that's x, how far away we go from being perpendicular. So to solve for this, this would just be a squared plus b squared equals c squared. So it's 3 squared plus x squared equals my distance squared, right? That's my distance I'm traveling. So this is going to be the square root of 3 squared plus x squared. So that's my time for rowing. My time for running, well, my rate is 8, and then I'm running this much over here. Well, real quickly, how much is that? Well, if from C to B, if that's 8 kilometers, okay, so if I go over an X amount, I have 8 minus X remaining. So for instance, if D over here is 2 away from C, then 6 is the remaining. So that's why it's 8 minus X. So this is just going to be 8 minus X. So now here's my function. Here's my time function. So my rowing square root of 3 squared, which is 9, plus x squared all over 6, plus my running is going to be 8 minus x all over 8. Okay? Now, since we're doing optimization, we want to find the minimum time. You can find the minimum time by taking the derivative and setting equal to 0. And you can totally do that by hand, but that's something that I'm actually not going to do. I'm going to do it all in calculators to show you. I also am going to do two things. So it's asking where he should land. I'm also going to add the question of how long it took as well. How long is the shortest time? And I'm only going to ask that because I have that access to that calculator. I just want to show you absolutely everything. So what we're going to do is fire up our bad boy right here. And we're going to go into Y1 and type this in. So I'm going to do square root of 9 plus x squared all over 6 plus, make another fraction, 8 minus x all over 8. And what I want to do is find the derivative. So second, this is going to be not second, it's going to be alpha f2. Go down to derivative. Respect to x, I'm doing this to y1 at x equals x. So this is going to give me, and I don't want to graph the original, I don't care about that. I want to graph the derivative and see when does it equal 0. So I'm going to go to my window. Now when I do my window, I do have a maximum and a minimum. This has to be, x has to be between 0 and 8. Okay, because if you look at my picture right here, since it's 8 kilometers away, I can either run 8 or I can run 0. So that's why I'm going to go from 0 to 8. So that's all I care about. Is from 0 to 8, and then I'm going to go ahead and graph this. Hopefully, my window is good enough here. Holy cow! Like I said, it's going to go really slow. You can kind of see it's kind of really tugging at that line. So. Going super slow. Let's just wait for it to go going very slow. Okay, so let's just wait for this. Awesome. So that really doesn't help me out so much, but again, I graphed my original here, and that's the derivative of it, which is really, really, really tiny. Okay, now I want to find the 0. So to find my zeros, I'm just going to go second trace, go to 0. It's kind of hard to tell where the 0 is, so if you can actually look at your y right there, that's going to really kind of help you where that 0 is. See how I'm at the negative y's there, and then now I'm at positive y's. So you kind of have to use that as a little trick because my window isn't great. I would redo the window, but then we'd be sitting here staring at that thing graph again. So I know I'm negative right there, which is the left bound. And then I know I'm positive there, which is the right bound. So boom, that's my 0. Okay, so I'm going to get, so when I take the derivative of x of t of x, okay, and I set that equal to 0, I'm going to get x to equal 3.4016. I'm just going to label out 4 of these. You only need 3 of them. So this is the work that I'm showing to say, I'm using the calculator, and I set equal to 0. I get that for my x value. Now I want to make a little bit of a sign chart from 0 to 8. Okay, at this 3.4016, I am negative, barely, but I am negative, and then I'm positive, which is confirming that, yes, I do indeed have a minimum. I could plug in my endpoints for the candidates test, but I don't need to. Since I made this chart, I'm proving that since I'm decreasing, then increasing, this is my lowest possible point. Okay, so that answered my how far does he run question. So where should he land? So he should land 3.4016 kilometers away from point C. Okay? Now, let's answer the second question. How long is the shortest time? So you need to take this x value and you need to plug it back into the original, and that will tell you the time. So let's go ahead and do that. So you go to second quit. If you go alpha F4 call up Y1, that's going to use the original function, which again I have in Y1. And if I actually just type in X, it saves the most recent X value that we have, which was this value right here. So if you just do that, kablamo, the answer is going to be 1.3307 hours is going to be the shortest time. Okay, so I added that question in just so you can see how useful the calculator is if you do it exactly this way. Plug into Y1, the original function. Don't have to graph it. You do need to graph the derivative, though. That's going to give you this answer right here. And then you can plug that back into the original to get how long it would take. And that is it.